Nice. So, okay, welcome back after quite long break for the lectures. We are back to a class of machine learning techniques and structural mechanics, and we already half passed the course. So we already had six lectures out of 7. So we out of 12, sorry, and now it's 7th lecture. And first of all, what have we learned, as usual, from the week 6? So if you remember, we worked with classification problems. Then we looked at detection and classification and localization. And right now, in general, in industry or everywhere, the detection and tracking of the objects and images is one of the most popular topics of machine learning. So we get familiar with the YOLO algorithm. You only look once, based on convolutions that drastically speeds up the problem of detection, localization, recognition, enabling even real-time tracking. And what we actually decided with Gerrit, that on the practice this week, we will play a little bit with YOLO algorithm. So if you will record any video before practice, we can individually, you can play with the recognition of the objects on the video. So I will remind about that at the end of this lecture, because it will be more interesting probably for you rather than just have some predetermined videos or images that we provided. So we will play with YOLO algorithm by ourselves during the practice run. So YOLO can be used for anomaly detection. We looked at it a little bit using different ways to detect anomaly in our systems. And of course, there are other supervised and unsupervised approaches for anomaly detection. We talked about it a little bit. And finally, one of the very cool architectures that was introduced last time was autoencoders, that basically unsupervised learning approach enabling the system to learn the most important features by itself rather than waiting for us to deliver these features. So yeah, and now we're going a little bit further. The topic of today's lecture is transfer learning, but before that, I need to formalize a little bit what have we done until now from the mathematical or probabilistic point of view. So actually, with supervised learning that we did for the 6 lectures or practices, what we did, we looked for the matching between instance space and the label space. So almost all supervised problems can be formalized in this manner. So we have the instance space where our objects live. So this is one of the objects, let's say having n coordinates, or it can be image, and we have quite a lot of pixel values there. And let's imagine that we live in some sort of Rn space. So we also usually have a label space. So for instance, I1 will be responsible for the cat, dog, or I don't know, some sort of crack, whatever. And what we are actually looking for the sort of target function that match instance space and label space. And usually when we have our trained data set, so we have this instance space here, and we have something like label space. So we can also do absolutely the same discussion for regression. So in this case, we don't have a labels, we have more or less continuous values. And for each xi, we look for yi. But in reality, our system may be a little bit more stochastic. So we, let's say we can label image in a different manner. So therefore, we actually may look around this point IY. So we have sort of target function that is noisy. So in this case, we may have something that we are looking in the vicinity, very loud sound, in the vicinity of this point yi. Is it clear? Basically, what we are doing, it's very basic idea. So we have this instance space where our objects lives, and we have a label space, and we would like to match them. However, we also can do it from a probabilistic point of view. What does it mean? So imagine that this is instance space. And this is our label space. And I draw it, of course, in one-dimensional way. So, of course, our instance space is usually much more dimensional than 1D, but I'm just drawing like that. So what we actually can, in this case, describe, we can describe the probability, it's called marginal probability, over our instance space. So what does it mean? So for instance, what I can do, I can say that if we look at all our objects, we can have some sort of probability over the x. So let me give you an example. Imagine that you have a dice with one, like basically you have some sort of dice and you throw one dice. One, I don't know, two, whatever. So, and if you get more than 3, you win. So your label will be 1. And if you get lower than 3, or like 3 or lower, then you lose. So in this case, label space, how many labels do we have? If you throw the dice, yes, and if you have more than 3, then you win. And if you have less than 3 or equal, then you lose. 2 labels, right? Win and lose, more or less, yes. So we actually have 2 labels. But how many objects, in this case, in instance space, do we have? Many elements. Exactly 6. So I'm just giving you the very basic example. In this case, we have 1, 2, 3, 4, 6. And if we actually draw the distribution, of course, it will not be very continuous because we have sort of discrete values. But it will be something more or less like, again, if then I will consider infinite amount of faces on the cube, it will be more or less straight line. But now imagine I'm throwing 2 dices. And now I'm not looking at them separately, but I'm looking at the sum of these 2 dices. Right? So, and then my rule is the following. If I throw more than 8, I win. If I throw 8 or less, I lost. In this case, we still have 2 labels. And since we are looking at the sum only, we treat that as one instance. So what will happen with my distribution, Px? It will not be straight anymore because we have a much higher probability to get 7 than 12. So in this case, our Px will look something like that. Yes, okay, not like that. It will look like that, right? Now that's important. It's called marginal probability, and this is the probability of our instance space. So what's happening next? It's quite interesting. So what let me switch it further. And let me draw some. Let's take some value x. And now, for this value x, I have some probability of the label I assuming x. So, and it will look somehow, sorry, I need to delete that. Okay, I probably will switch to the next slide. It will be better. It will be faster. So we have this Px, already draw it. And for x, we have some distribution of the targets, of the label. Of course, it can be discrete in general. So you can have exact, so for, let's say for the sum less, like if you have 2 dices and you get 3, then you lose, so your label is 0. But in general, it's more or less stochastic. So you have some distribution around the mean, and the mean in this case is this value, right? And then, basically, what you have joint distribution over the instance space and label space. And the task of machine learning, do you get what I'm drawing in general, at least approximately? It's not so important, but it's kind of, I need to introduce this particular value here. So we have the instance distribution as distribution when we look at what we have as an object and how often we see these objects. And we have, for each object, we have the target distribution. So how far, like basically what's label or what value is corresponding to this distribution. And then from the statistics, what we can do, we can write joint distribution P of X and Y. So we calculate this distribution on the both domains, on the instance space and the label space. And in this case, it can be written as a probability on instance distribution and conditional probability on Y assuming X. Have you seen this particular thing from the statistics? Are you familiar with this way to write this conditional probability? No? So are you familiar with this? No? Okay, in this case, I will simplify that. Okay, so we will not go deeper in this case. So the idea is that this is a probability, like when you calculate the probabilities in general in statistics, if you just look at the process itself, this is exactly the probabilities that you're all familiar with. So the probability to throw 1 on 1 dice will be 1/6. The same with probability 2, and so on. But there is a conditional probability. So this is a probability of some event, considering that another thing already happened. So considering that there is another condition, that's why it's called conditional probability. But okay, in this case, since you are not familiar, I actually expected you to be familiar with that. So in this case, basically, I will summarize it like that. So we have our data set, we have our x's and our i's, and usually we have n of them, let's say. So this is the x's, there is a y's, and we either can say that we sample them from x's from the probability of marginal probability over x and xy of the function that basically match x's and y's, or we can also say that basically we are sampling our pairs from this joint probability under some assumptions. And our goal not only to estimate f, as we already know from previous slides, so we try to find the matching, but also where can we reframe it when we say, okay, we actually try to find this PYX. So probability, we would like to our model to learn not maybe exact value, but the probability to get a label assuming the specific object. So that's exactly, imagine that we have, again, 2 dices, we throw them. So what is the probability of winning, assuming that we have x equal to 4, 5. So we have a dice 4 and dice 5. Our probability in this case would be 1. So if for x equal to 1 or 2, our probability, like our probability of winning would be 1, and our probability of losing will be 0. So instead of talking about the functions and about the exact values, we can talk about probabilities. But again, since you are not familiar with statistics, let's just try to remember that, and we'll not return back to that. Okay, so that's a thing. So now let's go to more picturesque explanation about transfer learning. So what we did previously can be summarized in this particular picture. So imagine that we have objects, triangles, on the left. And our task is to detect which objects are wider than, which objects have a larger width in comparison with the height. So we can simply train the model. We basically have 3 coordinates of the corners, and we can train a model that basically tell us that, okay, these 2 examples are very wide. So we consider them as a positive. And this will be considered as negative, like label 0. And now if I will give you another task, so let's say 0, 1, 1. Let's take a look at rectangles. Now we have 4 inputs, we have 4 corners, or maybe you can define the rectangle in a different way, let's say width, height, and the coordinate. We cannot use model R anymore, because model R requires 3 inputs. So we need to train model B. And then model B will also work very nicely and say, okay, this is definitely wide, and these are 2 actually not. So do you think it's a reasonable thing to do? I think intuitively we understand that there is some way to use model A to help us to solve the problem on the right. And that's exactly the domain of transfer learning. So we want to get a knowledge from the model A and somehow apply it to the model B. Okay, that's a core idea, core concept of transfer learning, right? So for unsupervised learning, you had experience already with that. What can you say about test and train data sets? You did a practice. Come on, Windows. You did the practices when you kind of work with images or work with numbers. What can you say about train dataset and test dataset? Okay, that's good as more or less practical thing, but more globally, like if you look from the fundamental point of view, your train dataset, like your examples that go in, like samples that goes to the test dataset and samples that are going to the train dataset, they're separate, but it doesn't matter that they're similar. They're from always assume that the data set, the train and test sets are both from the same distribution and from the same domain. So remember how we did it? We gather data and then we just split it. So we have the same data. And also, again, surprisingly, we usually assume these probability things. I will skip it, that they are not only the same shape, but they're also from the same distribution. It's more generic way to think about that. And both sets are labeled, so you are absolutely correct. So we have two things. We have two things that we know about the test and data set. But what if it's not a case? So you see, this is a very, very sort of synthetic example when we work with these images, and we are happy to have both of them labeled and both of them absolutely the same. So we train our model on the same data that they will use it later. So for example, what if we train our model on the holes and then we ask to classify cuts? Or in more generic case, will you train this model during the practice and it recognizes numbers very well? What if you will try to apply it for another data set? This is a data set assembled by the Google. It's its address flags from the Google Street View. You see that basically it's still numbers. But if you just directly apply this model, you will fail. But at the same time, you don't want to lose some knowledge. So you right now know, like your model knows how 9 should look like, or I don't know how 7 should look like. So there is probably some way to use already trained model on this new data set. And that's exactly, again, I'm repeating myself, the goal of transfer learning. Okay, let's define a new term. Oh, that's interesting. This thing should have a little bit different way to be written, but this particular computer doesn't have the font that I used. Okay, so we need to define domain, and domain is the feature space. Feature space is actually representation of your objects. So for instance, for the images, for the color images, 32 by 32, our feature space is 32 by 32 by, let's say, 3. Right? So, actually not 3, honestly, 25. So if we have so much colors, so it's our feature space. Right? So it's like where we sample our objects from. So this is more or less everything that we have. And then we have also probability distribution over this instance space, more or less. So it's exact images that we are using, but for the probability point of view. And this is there. So this is a domain, what is called domain. There is also another term, task. Task is a combination of the label space, and you can easily imagine what is label space. It's like set of the different labels: cat, dog, I don't know, crack, hole, whatever. And also this conditional distribution that we try to learn during machine learning. So during training, again, we'll skip it since you are not very familiar with the statistics here. So, and we know that during the training, what we learn the target function or this distribution from the training set. But what if our task domain and train and test sets do not match? Then we have a problem. Then it doesn't make sense anymore if our train set and the test set will have a different domains and different tasks. We cannot use supervised learning. It's exactly what will happen if you take these numbers and try to apply them for these address plugs from the Google view. It will not work. In this case, what we're saying, we have a source domain and source task, DS and TS. It's a thing that you have in your training. It's a thing that you have in your training. And let's say this is this MNIST data set. And what you also have is a target domain and target task. It's something that you want to do on a new, let's say, on the new images, or maybe you have a different task. You did some classification, and now you want to do something else. So you have the two different entities, source domain and tasks, so source things, and target domain and tasks. And transfer learning deals with learning a new target function that is actually applied for the target domain using knowledge of the source domain and source task. It's again, this is more or less formal definition. And usually, why we are doing that? Because target domain is much nastier. You don't have enough samples there. Sometimes you don't have labels, and therefore you cannot use classical supervised learning on the target domain. And what you are trying to do, you are trying to train it on something else, and then use this knowledge to help you in the target domain. Do you get the concept of that? So we have sources that you can easily train, but then you want to use this knowledge somehow to apply for a real, let's say, application. Okay? And here we have a couple of different options. First options that we can have same domain but different task. So let's say that our we remember the task is consisting from the probability and label set. So in one case, okay, we have the same domain originally, so the same, let's say, images, but a different task. And for this task, we assume that our label space is different. Can you give me an example for this particular situation? Come again? Yes, but unfortunately, in this case, do you have same domain? You don't have same domain, unfortunately. So it's a different things. Same domain, basically completely. Let's assume that we have completely the same pictures. We have completely the same set of pictures, but our label set is different. So what you can imagine, there is actually two data sets, the same images, but in this case you have only 10 classes, and you have another task for these images, another label space, different task, in this case different label space, when you have 100 classes. So you can see that probably somehow if you have this model trained already, maybe you can use the knowledge of this particular model to help you with this 100 classes. So that's one of the examples. It's quite a rare example, to be honest, but it exists. So if you have a different label space, so you have in this case 10 classes, 10 labels, and 100 classes. There is another thing when the probabilities are different. So what we will not stop on that because it's quite rare, and honestly, it's not so interesting. Much more interesting problem is when we have a different domain and the same task. So remember, domain is a set of the feature space and the probability of that. So in one case, what we have, different feature set. Let me just show you in this case. So for instance, remember feature, it's a way to represent our data more or less, if I simplify it. So for instance, in this case, this image has, I don't know, 400 by 200 pixels by 3 channels, and each channel have 20, like this number of values. And we consider gray scale image. So it's the same sort of image, but a different representation. Or we can think about the text in the different languages. So in this case, we have the different domain, same task, let's say classification, and we have a different feature space. Okay, but it's again, this is not so interesting. The most interesting case is when we have different distribution of the samples. And now we will see what do I mean here. So imagine that you train your model on these images. It will be your source domain. You see, you have the same task. Classify me, let's say, what manufacturer of this car is. BMW, yes, BMW. But you trained everything on these strange cars. And now you would like to do the same task, classification, but using a different domain. So you actually, it's usually case one, it's this one plus you still have a different feature. Usually they're going together. So you want to go from this source to this target, right? So, and of course you can use some knowledge that you gain here. For instance, by looking at the shape of the car, you can maybe deduct that, I don't know, this is not BMW. It's probably Volkswagen, I don't know. So it's called domain adaptation. So we have a different domains. We have a different domains we are trying to work with, but their task is the same. Another example, for instance, is when we train everything on this MNIST data set, we learn this 6, whatever, but now I say, okay, there is another, this is MNIST data set, and there is another alternative data set, it's called MNIST-M, and we will see it in a couple of slides. And this is color images with some random background. So someone just manually or maybe automatically did a little bit of modification of MNIST by adding this background, right? So in this case, if we train model on these images and directly apply it for this image, for this source, target, even if you achieve, let's say, 98% accuracy that you did actually during the practices, here you will get only 57%, because your model will try to look at the color, and color doesn't matter here. What's matters is the shape. But you have so much information, so your model will try to look at the colors, and you cannot use the same model for the for this MNIST-M. Another thing, when you have these different domains, is quite cool. So this is a photo from GTA 5, from the computer game, and it looks very similar to the real life. So you can use the simulations in GTA to then train your models on the real images. So you first train everything in simulations because you have better control, and then you transfer learning that from this, again, in this case, that's our source, and this is our target. And you shift the domain from the source, like game things, and therefore you expect different, I don't know, probability to see specific houses there or so on, and then you use that for the reality. So the domain should not be very different. So that's why kind of the feature, that's why I assume that the task is the same or so on. They should not be very, very different. But at the same time, they should have some differences, otherwise what's the point? So you can take this game and then train it for the real data. And that was done, and it's working very, very, very cool. That's actually also working for the autonomous driving. So Google, for instance, before running the autonomous cars on the streets, they did that in the virtual reality in simulations. So they recreated this virtual city, then trained on virtual city before moving to the real roads, because you have some similarity and you can train it and then use transfer learning. Okay? So basically, when we can use transfer learning or domain adaptation, another term very tightly related to, similar model was already trained on larger data set. We didn't discuss that, but I think I mentioned from the YOLO perspective or from the other image models, they're extremely expensive to train. They have millions and billions parameters, and you cannot do it on your computer. You cannot do it probably even on a cluster that we have here in university, or you need to pay a lot of money. So in this case, if you have a similar model that's already trained, why not to take this model and just transfer learn our new data set? For instance, you have the model that knows how to recognize cats. Why not to use this knowledge and recognize dogs? And I will show you how it works on the next slide. Another thing that why we need to use transfer learning in many cases is we don't have enough labeled data in a target domain, or we don't have labels at all. That's quite common situation when we really do not have labels, or you need to hire someone to label it, and it will be quite expensive as well. And finally, you have a better control over the input samples in the source domain. You know a little bit better what's happening in your source domain, and you have a control over that in comparison with what's happening in, let's say, real life or your target domain. Let's say a Google car example. So and now, basically, how does it work? So this is there is another term for that, fine-tuning of the models. So if you have a very big model, and in this case we consider model called VGG19, it has 19 layers and 143,000 parameters. 143 million parameters. Sorry. Where are you going? So and then I can feed image from an ImageNet dataset. It was absolutely random that there is an image that will be recognized as so this dataset, ImageNet dataset, contains 1,000 classes, and two classes that actually exist in this dataset. It's a beer bottle and a pizza. I don't know actually what will be picked from this dataset using the training, but let's say it will be beer bottle, right? So you know, and this model is trained on this ImageNet dataset, and this is more or less common image that we have. But now imagine that your task is to detect new images that, of course, do not belong to domain of the ImageNet dataset. No one will put these concrete cracks inside of the dataset. This dataset is quite massive, but it doesn't contain the cracks. And your task right now is to detect if there is a crack or there is no cracks at all. Or in other case, you have some CT image, and now you need to process that and learn that if the patient is healthy, if you see a flu there, some pneumonia, COVID, or something that will happen next year, no one knows. So the thing is, you either need to train it from the scratch, but that will be a problem, since how many samples will you have? Maybe you will be lucky and have 10,000 of them, but if your image is large enough and complex enough, it will be not enough to train the model. But you already have something that is trained on millions of images. Why not to use this model and just train it to recognize what's happening with the CT or with the cracks? So let's look at the CT in this case. What will happen if I will do the same model with the same? So basically, we have these parameters. Therefore, we have a lot of filters. So we use these convolutions. Again, there is a couple of channels. There is more channels. There is even more channels, and we have the flat dense layers. Then, what will I do if I will do the same model? If I'll apply for this CT scan, what do you think will happen? The model is trained to classify one of the 1,000 different classes to basically recognize what is on this image and basically give the highest probability to one of these classes. So what will happen here? Probably it will predict that this is a wall clock. I don't know. I didn't check it. So it's useless for you. It's really you don't want that. So that's definitely useless. But now you smart and you're saying, okay, what if we will freeze these layers? So why training is super hard? Because we have so many parameters, and each layer contains different number of parameters. For instance, if you have let's say 400 filters here, and each filter is, I don't know, 10 by 10, then you have 4,0,0,0 parameters in this layer. Then you have another layer and another layer. So you have different number of parameters in different layers. And training is hard because you need to update all these parameters. Remember what's happening during training? We do this back propagation, and the weights of filters, basic filter elements, change over the time during the training. Do you remember that? Agree with that? It makes sense. Makes sense. So now you're saying, okay, but what if I will just look only on the last things? Maybe it will have, let's say, 10,000 parameters, maybe less. What if I say, okay, I will not train these things, I will take these filters as they trained and then just retrain the last part of my model. And that's exactly what you do for the transfer learning. In many cases, you just freeze these layers that they are deep layers, right? Shallow this one, or get it, which way? Yeah, okay. So I don't remember really well. So you train the first layers, you freeze them, you do not touch weights there, you do not touch filters them. You believe that the filters will be absolutely the same for the CT image as for this ImageNet data set. And you say, okay, but what I'm interested is to change something, and you change only the last weights of the last. And then, depending on your problem, you can maybe freeze all convolutions, or maybe you can leave some convolution also to train. But in generally, you freeze them and do not touch them, and you update everything here. So basically you take the initial model that's already trained and you modify it. Or, again, that's why it's called fine-tuning, you fine-tune it. The great question is, why does it work? We have a different domains. We have the city images that has nothing to do with basically this beer and pizza. And if you remember, on one of the lectures, we looked at the paper when we had the inclusions inside of the volume. And one of the images that I showed you was the outputs of layers. When we go from the very deep layers at the beginning of the neural network, so in this case input layer, going to the last layers. And look at that. Early layers of the model learn to detect very simple features. In this case, they recognize the circles. And then you're going through this neural network, and more complex features start to emerge. I will show it on the next slide. For instance, this is a good example from the GoogleNet network. So this is the first layers output. When you apply filter for this first layers, you see that the neural network detects more or less just lines. Lines in the different directions, but then you go deeper, you go through the neural network, and your next layers start to recognize textures. You go there, you have the patterns, then the farther and farther you're moving, more and more complex things your model can recognize. It looks at the parts, and finally already objects. You see some eyes, you see some dog face here, for instance, I don't know, some human legs, whatever that is, at some buildings. So therefore, these layers at the beginning, they are very good in training the filters that will recognize simple things. And if you remember from one of the lectures that we did, remember our filters when we detect edges. So we had this filter, if you remember, it's called 000111000, and we did convolutions, we recognize very simple things. And that's exactly the filters that is getting learned during the training at the first layers of the model. And now it gives us an answer why the transfer learning, as we are doing it when we freeze these layers, works. Because regardless of the image of the data set, we always have straight lines. So therefore, if we have a straight lines in this image with the beer or the pizza, we probably have straight lines for our CT images, or maybe some curved lines. So the thing that we already have the filters that can detect the basic features. So then probably we also have some textures in our images. So why we retrain these filters when they're performing very well already? They can detect the textures. So what we need only to do, it's like, okay, stop recognizing dog faces or eyes. Let's start recognize the things in the CT. So we say, okay, we get rid of this last layer and retrain it. So now, because we are not interested in these particular things, we're interested in the specific labels that we attach to our CT images. And that's exactly why transfer learning works, because our layers at the beginning learns very basic features. And if already they are capable of doing that, why do we need to retrain it? We don't need it, we freeze them, and we just retrain the last layers. Do you get it? Do you get the main approach in transfer learning when we freeze the layers? Great. So now I will check how have you listened to this lecture? How basically did you pay any attention? I think like Atul is not. He's a little bit sleepy. And I will give you a challenge. This is a colleague of ours, David Labonte. He is working in Imperial College London, and he's doing amazing basic work. He's interested in evolutional biology in relation to mechanics. So one of the projects that he is doing, he's studying ants, and they even build a device that measure what's the force generated by ant when the ant bites the leaf. So his research is in so-called leaf cutting ants. We don't have them here in Freiburg, but they are more popular in hotter regions. So, and the idea that depending on the leaf density, on the leaf mass, or the leaf structure, the ants can take a different bites in order to actually optimize the cutting process. So, and this is quite amazing research. But another problem that he had was with the tracking of the ants. So because if you have a lot of ants, you want to follow their trajectories and processes somehow centralized, and maybe you should build some database, or I don't know, just tracking the ants. So basically, if the ants are living on the very flat surface, you can use YOLO model, really directly YOLO without any additional training, that will detect, that will then draw basically rectangle, so it's localized. And you see it's saying ant, and there is a probability of this is ant, it's 95%, more or less. So, and then follow and track these ants. And also what he is doing here, you see these small dots, it's called pose estimator. So it's not looking at the ant at the point, it's looking at the legs of the ant, it's looking at the antennas and everything. So, to recreate basically skeleton. So, and this is another very nice image with multiple ants with the leaves. You see they're eating these leaves. And here you have all these ants kind of separated. And this approach of the tracking with YOLO works quite well if the ants live at the flat surface. So you have this nice white background. It's quite easy to detect ants. Of course, there is some confusions when they kind of intersect, but in general, that's not a big deal. But what they wanted to do is much more complicated. They wanted to track the ants in real three-dimensional space in a forest. So this is an example when you have this, I don't know, tree branch, and you see ants are moving there. Right now, your conditions are very, very hard to control because really you have the depths, you have different colors, you have the textures, and it's still very nice to recognize in 3D and follow them in 3D, these ants on this branch. And my question to you would be, so if you remember YOLO, think, remember this vector, output vector was PS, this is if we have object or not. Then we had bx, by, bw, bh, it's our rectangle. And then we had our class 1. Let's say in this case we will have only class 1, it's like ant. So we can actually get rid of that and say PS would be 0, no ant, and 1, if ant. And we train our model, YOLO model, for instance, trained on exactly the dataset. Dataset is called YOLO, is partially, I would say, on, it's called COCO dataset. It stands for common objects in a context. And this dataset contains not only the labels, but also rectangles. So it basically tracks the position. So in this dataset, all things are represented as this vector, PS, and the 4 coordinates. So let me just write it in a little bit better manner. I changed the color. Why it haven't changed? So, and since it was trained in usually these objects have a very good background, it's quite easy to use YOLO for the ant tracking. But now we know the problem. We have a 3D space. We have different textures. We cannot just reuse this white background for the tree. You understand that, right? We need a labeled data set. And now this is a challenge for you. How would you approach that? Think about that. How would you create a labeled data set to track ants in a forest or in these non-very controllable conditions? Because you need images, like sort of from the camera, that will capture different trees, different stones, different size of ants at a different distance. How would you do that? Any ideas? I will actually, I will give you a challenge, and now I will wait for a couple of minutes for you to come up with this idea, because I think we already mentioned this idea during this lecture. If you kind of paid attention, you probably have a solution for this problem. But there may be multiple solutions. Technically speaking, there is no one solution. How would you create the labeled data set in order to train your classifier and tracker or like detector for this particular problem? Oh yeah, again, yes, it was quite fast. I expected you struggle more, but that's exactly the right answer. What they did is quite fantastic, because of course you can hire, I don't know, 10 students and just go through each frame of the video, cut the ant, draw a rectangle, and then use that. Because you probably need, let's say, 100,000 images to more or less be confident, because you need the ants of different sizes, of different colors. And again, you hire students, they work for a year, 10 of them, you're paying them salary, they're bored as hell at the end. I don't think that's a good idea. What they did, it's quite magnificent. First of all, they built a little bit of device, see this, that sort of scan the ant geometry. Or real ant, they put real ant and they scan it. And then using Unreal Engine, they recreate the artificial environment. So they put, as usually, if you are familiar with the rendering, with all Unreal Engines, with the blenders or whatever, so you create lighting and camera, you put ants on them, then you create some materials, you create the different reflections, you have a different textures, then you put some objects like stones or, I don't know, some trees maybe there, you change a little bit topology in order to not make it flat, and at the end you have a very procedurally generated environment. See, you really have something that looks like a real environment, but of course it's computerly generated. And what's happening next, you really just imagine that you are taking the image from this virtual camera, because that's exactly how it's working during rendering. You have this camera that's looking on your scene, and you process that. And my question in this case, okay, you have the images from the camera. Where did you get an object coordinates? How do you know that ant is in exact position? Yeah. Yeah, exactly. It's because you know in 3D space, because it's computer generated ants, you know the coordinates of the central of the mass, let's say. So you really just track this. That's a beauty. In real ants, you have no idea where the ants is. In a computer generated ant, you know exactly where it's located in the 3D scene. You know exactly where your camera is located, and you can match the coordinates of the ant with the image of the camera, and it will help you to recognize. Yeah. Yeah. What else? There is a problem when you have the ants that are intersecting. You also have the leaves that can move. So again, there is no other animals there, and generally it's more robust, because it's closer you are to real life, the better your transfer learning would be. So that's exactly what they try to replicate, basically real life, and that's actually images. It's artificial images. This is image from the game. Sort of, you have a camera. I don't know why they have the slide here, but they really did very, very cool job by recreating the real life. And at the end, what happened, this is an image. There is another task that they did, I would like to say, when they wanted to track, when you play these computer games or you use this Kinect or Oculus or whatever, it tracks your position of your arms or fingers. So they wanted to do very similar things for the ants. They wanted to really create this pose tracking, so how ants is moving. And when they did it only in virtual reality, and then tried to use model without doing real transfer learning, just basically copy it, they had a little bit of problem. You see, this is ant. It's actually not ant in this case, it's a stick insect. And only now the system picked up some parts of this ant, trained on synthetic data. And now what you will see will happen. You see, it's quite shitty. But then you refined on 5 hand labels. You hand labeled only 5 frames, and now it's much better. This is another image. This is without transfer learning. It's just learned, and now with handheld frames. I will repeat it again. So you see how good the tracking is when you use a little bit of training from the real life. So again, you cannot directly use computer trained model. You just need to do a little bit of transfer learning, and for that you need to have a little bit of examples from real life. In this case, it was enough to use only 5 frames to do that. So you see, this is quite bad. And now refined on 5 help, and it's perfect tracking of the all ants legs, and you can really play with that a lot. Again, this is without proper transfer, and that's with a proper transfer. So much better results. And again, only 5 frames. So that you can do in a minute rather than 1 year for 10 students. That's the beauty of transfer learning. So, and this is actually the process itself. There is a summary. I would like actually to stop the video on one point, just on this point particular. Just, you see, YOLO version 4. So it's available for everyone to use in general, and it's super powerful thing to work with. So that's how it's a little bit of summary of the work that's published as a preprint, and I uploaded this preprint to our Ilias, so if you're interested, just take a look. It's really easy to read, no mathematics at all, just the process itself. It's really interesting paper. I really recommend you to read it. So this is the big ants, small ants. They intersect somehow. There is the image that you already saw. This is different lighting condition, and it's also important part of the transfer learning when you train your models in the daylight. Oh, this is amazing. See, the environment is very, very sophisticated. So lighting, it's a very big issue, because when you train your model for, let's say, for the autonomous car in a good conditions, then you need to be sure that your model will work during the night, and during the night your domain will change. That's why you need to do this domain adaptation. Okay, so that's the beauty of ants. So there is always a solution of your problem with not enough data, and one of the good solutions, if you don't have enough labeled data in the real domain, then you just can try simulations. So please read this paper. It's very recent, 2023, as you can see, and it's really well written. It's really, really exciting reading. So yeah, now from the ants, what time is it right now? Oh, good. We're in a good track. We may have a little bit of another problem that we didn't discuss during this ant example, but that's actually a problem, because for the ants, we don't actually have a labels at the end. For our target domain, we don't. And we just have like it, they are working. So there is a more direct example what will happen. So there is a MNIST data set that you are familiar with, these numbers. And there is a modified called MNIST M data set. And this is, again, numbers in the different colors on the different textures. And we right now assume that there are no labels for this particular data set, right? There are, of course, labels, but now we assume that our model doesn't know about that. So in our task is to train our model to work well on MNIST M dataset. And I was already mentioned, if you just train model here, and then it will be 98% accuracy, and then you apply directly, what you will have 57, if I remember, % of accuracy. It's not enough. So that's a problem. I already announced it. So the thing is, the second domain, these examples from MNIST-M contain colors and textures. And our CNN, when you will do training, will actually will pay attention to the colors. But we know that colors are not important. We know that what's important is the shape. So we need we need a way, yes, to force our CNN to ignore colors and care about shapes only. And here we have so-called domain adversarial training. It's maybe will be not so easy to understand, but it will be only one slide, and I think I will be able to give you a very nice example of that. So adversarial means that there is something fighting against something. So you will, in a couple of lectures, you will hear about generative adversarial networks, when you have two basically things, like it's called generator and discriminator, and they're actually fighting against each other. So for instance, generator tries to fool discriminator by giving a fake data, and discriminator tries to learn not to be fooled by the generator. So they are working against each other. So here you have a very similar concept, but for the domains. So this is a paper from 2015, and this paper, I looked at that recently, was cited more than 5,000 times. So it's very fundamental paper. And the idea, again, we already know that our goal is to force our model to ignore the colors. And what's happening in this case? So in this case, what we're adding, so this is, if you look at only the top layer like that, it's our classical CNN. We have convolutional layers at the beginning. So the convolutional layers, sometimes you call it feature extractor. Basically, what we are doing at the end, we just form the important things from the image, and then we do this label predictor or classifier on the like blue color. And this is a classical way. If you basically close this thingy here, and you apply it on your MNIST, and what you're feeding there, you're feeding to this during the training, MNIST plus labels together with MNIST M, but MNIST doesn't have a label. So what's happening here? You have additional thing, and you have additional loss function. You see, you have at the top, you have this loss that we are familiar with. It's probably some sort of cross entropy or whatever, binary cross entropy or softmax. What's happening here? What the bottom part of this neural network does, it's try to learn which domain your image belongs to. If your image belongs to MNIST or MNIST M. So if I will simplify that, and I just draw the bottom part without this fancy thing with gradient reversal layer, what will happen? I will take the image, I will go through some convolutions, then it will go to the flat layers, and at the end I have only one input, and input 0 if MNIST, and input 1 if MNIST M. If I just consider only this particular neural network, do you think it will be easy to train it? And I feed just images together. I will feed MNIST and MNIST M with labels because we know which it belongs to. Do you think this model will be hard to train? You're absolutely right. It will be easy to train. It's like it's nothing. So come on, you just have two classes for image, sort of black and white or color. It will be extremely easy to train, and it will be almost perfect accuracy. But we actually don't, and again, if we do it standalone, but in this situation, when we combine everything together, we actually don't want our model to learn the difference between the domains. Because if we learn the difference between domains, we start, what's the difference between these domains? Like as the person who are looking at these domains, what is the difference between these domains? Colors. So what it's actually learning if we do that? It learns colors. It learns to distinguish them by colors. And that's what we don't want. We completely don't want to do that. So what's happening here, it's absolutely amazing solution. Here, the researchers added gradient reversal layer. So you see minus sign here. So what's happening? They try to make the model to be as bad as possible for the domain decomposition. So you want your model to classify numbers, but not be able, because you see, this is the beginning part is the same. You want these filters to ignore colors. You want to make your model very bad in recognizing colors, because if it would be very bad in recognizing colors, it will be much better for the shapes, because it will pay attention for the shapes in order to actually minimize this loss function. This is an amazing thing. That's exactly how process works. You train a classifier for the labels, only source domain, because we don't have labels for the target domain. Target domain, of course, in this case is MNIST-M. Train domain classifier for the both domains. And you, instead of minimizing, you are maximizing the loss on the domain classifier. You want your model to be very bad in distinguishing of domains. And then you, of course, together you minimize the classification loss on the source domain, because you still need to recognize numbers. And that's actually an example from another paper. Basically what happens, if you don't, it's called domain confusion. You want your model to completely confuse the domains. Should not be able to distinguish the domains. So if you train it without your domain confusion, you see that basically you have the two domains, like one and first, like red one and blue one, and models spend a lot of filters, basically a lot of information is invested in separation of the domains, and that's what you don't want. So if you add this gradient reversal layer, you actually can force them to be basically at the same position, and therefore colors do not important anymore, and your model performs very well on the shapes. It's a quite neat way to do that. I really like it. Again, mathematically, it's also quite easy to explain, and you can even program that, but we will not do that because it requires a little bit of functional definition of the layers. Of the functions inside of the model. So, but you should understand that in many cases, there is a neat tricks that allows you to solve specific problems. And that's what we will see on the next example. So here, our example is to, okay, we would like our model be very bad at specific task in order to perform well on another task. It's important concept of this domain adaptation in this particular case in domain confusion. Yeah. The thing is, we agreed, I understand your question. We agreed that we don't have the labels for the MNIST-M. How you can mix data sets if you don't have labels. So that's the beauty of that. You don't have labels at all for the second data set. So of course, if you will have, you can just run them together. It really doesn't matter. In this case, it will learn a little bit better to really focus on the shapes. No. In this particular case, again, this is only two examples from this MNIST data set, but if I go a little bit back, you see that in many cases, the images, even at the background, you have different colors within the digit, and there is a much worse examples when you cannot. If you do this thresholding, you will fail. Again, in particular here, how you threshold it? You threshold it by knowing that it's yellow, because brightness here of the blue and the yellow is the same. So if you threshold it by the brightness, you will have all black image. So no, that's, again, probably you can somehow process that, the trick thing system or whatsoever, but in general, no. In general, you cannot do for this data set, just a simple conversion to the previous one. So, and the conversion actually to the previous one should be based on the shape. And that's exactly what machine learning is training. So at the end, actually, you can use this model to sort of to convert one image to another image. So, but it cannot be done manually. Any questions about this? So in this case, the last part, a little bit faster. than usual, but I think we are good for the last very neat way to train models. This is what we did. That's what we learned. It's a very neat way to domain adaptation even without labels. So you maybe heard about these terms like few shot learning, one shot learning, or zero shot learning. It's very popular right now, and you need that when you're unlucky. What if you're unlucky and you don't have a lot of data for both domains? So for both domains or for multiple domains, you just don't have enough data, and you cannot, let's say, simulate that. So you are kind of screwed. If you use classical convolutional neural networks, you will have a problem. Why will you have a problem in this case? Let's say you have 10 images of cats and 10 images of dogs. Why cannot you train classical convolutional neural networks, a network with these multiple layers and with a classifier output 0 if cat, 1 if a dog? Why do you think it will be problematic? No, let's say we have only image, like we will not have other animals. So you have just 10 cats and 10 dogs. And then you would like to build a big neural network that will classify cat or dog. Why do you think it will be quite problematic if you have only 10 images of the cats and 10 images of the dog? That's kind of also the case, I would say that, yes. But in general, Gerrit gave you a nice lecture about overfitting or underfitting. And in this case, honestly, if you will have 10,000 parameters and only 20 samples, you can fit whatever you want. It will be overfitting as hell. So you will have nothing of importance. You will really learn to very confidently say, this image that I've already seen will be a cat, and this image that model already seen will be 100% dog. But it will not generalize well, because again, you will have overfitting. So then that's exactly the problem. So let's say we have like 10 images of cats, and let's say that we have some images of dogs. And now I have another image, and I'm asking you if it's, or not you in this case, I'm asking neural network, if it's cat or dog. So of course, we cannot really train our classical CNN models. So, but there is a very neat trick. We can look at the differences between the class of the dogs and the class of the cats. So technically speaking, that's how we recognize like different classes. We look at that, okay, does it look similar to the dog, more similar to the dog rather than to the cat? And we never use that in training until now. And now I will show you a very neat architecture that is called Siamese architecture, Siamese neural networks. In this case, what's happening, you have one image, let's have the cat, and you have another image. In this case, it's called anchor image. It's just any random image from the data set. And it can be either positive or negative image. What does it mean? If it's positive image, it means that it belongs to the same class. So it's a cat. If it's negative image, it's a dog. And your input in this case, your input contains two images, not one, but two. So, and we have image 1 and image 2. And we run them through the neural networks independently. And as you already probably guessed, the neural networks are absolutely identical. The top neural network and the bottom neural network have absolutely the same weights. So that's why I highlighted them by green. So they're absolutely identical neural networks. Why that's why they're called Siamese. And what we actually have as an output, we have a label. But now our label is not a cat or dog. Our label is if the same or similar or 0 if they're different. But right now we don't care about cat or dog. We just care if our pair of images is similar, the same class, or different classes. And that's quite fascinating. In this case, what we can define the so-called contrastive loss. Sorry. Remember we did this binary cross entropy or whatever. Now it's different. So now we have our ground truth label. Let me check if actually I'm correct in terms of what is 0 and what is 1. 1, 1, 0. What did I say? Why 1 is the same and 0 is different? No, I think 0 is the same, sorry, and 1 is different. So our contrastive loss in this case will be combined from the two different parts. And here, what you see here, it's actually distance between this vector and this vector. So it can be either Euclidean distance between vectors, or it can be some more sophisticated cosine difference for specific cases. But in general, you just assess the difference between these things are called embedment. So you have, instead of images, right now you are looking for some vector at the end, because at the end it's a vector, let's say 10 values that will have a the vector with the 10 coordinates. And you will see the difference between them in 10-dimensional space. And you define this particular loss, and you train your model. You really just take the pairs of your cats and dogs, or cats and cats, or dogs and dogs, and run through that multiple times with this particular loss function, and you will actually get a very nice results that will allow you to sort of to distill the features, let's say, of the cats and feature of the dogs. So do you understand how this concept looks like? So right now, you are not feeding one image during the training and then say how similar it will be to another image. Let's say what you are doing right now, you're just feeding pairs of images. And as an output label, you'll see it's the same class or the different class. There is even better way to do that. It's to feed 3 images simultaneously. In this case, you have this anchor image. Again, it's any random image. Don't look at this particular cat. Then you have this positive image, so it's the same class, this cat, and you have a negative image, the dog. And then you have a little bit more different, triplet loss. And again, this is D. It's a difference between output of the anchor, the top one, and positive. And this is the distance between anchor and negative. And you want actually to expand the difference between anchor and negative, and you want to decrease the distance between anchor and positive because they belong to the same class. And again, you compare that, you use this loss function, and you will get quite amazing results. So where such architectures can be useful, they are really useful for face recognition. If you need to basically to recognize it, especially for if you enter the building and the camera looking at you and would like to see if you has an access. So this particular recognition. Fingerprinting, or also to assess text similarity. And this question, why this is called one-shot learning? Do you have any idea why it's called like that? Yes, exactly. So what's happening, it's very important. You have a trained data. Let's imagine all of us will be in data set, or our faces. So we have, let's say, 20. We have 20 faces, and in this case, let's say we have 20 different classes, because each class will belong to, like, basically, you have a person who belongs to the class. So we have 20 classes. And now you have your model, so the take image of your, I don't know, face, and then transform it in so-called embedment. So at the end, you have, let's say, 10 value vector. It's the last output before you start to compare them. So, and what you are doing, you just, and here between these things, you have your model. And we have the 20 faces, 20 classes, 20 models, and then I pair randomly, let's say my face with the face of Naim, and I would like to say, okay, we are in the different categories, we are different classes, and then I have maybe 2 images of my face. I have like profile or and fast images, so I do it for my image and my image again. And what model learns, it learns to distinguish people as much as possible. So to focus on the most distinctive elements of the face. in order to be successful in terms of assessment if it's the same person or not the same person. So that's exactly what's happening. And now, when we train this model, now imagine that we have very good timing in other students coming in. And now, what I will do, I will take the student face. I don't know. Maybe he will have, okay, let's say glasses. Doesn't look good. And I put it through the already trained model. I do not train the model. This is a new class, probably. So I don't know. Maybe it's someone who already in the system. And I put that through my model. We have training here, and here we don't have a training. And it gives me another 10 value vector. And what I can do right now, I can say, okay, so I have already 20 vectors for students. And I have one new vector. I can take this vector and compare it, how far this vector is from already existing ones. So of course, we will never have ideally the same picture, but considering that our model right now focuses on the most distinctive parts of our face, what will happen if I will see a distance less than some threshold? So we can imagine that it's actually 10 value vector is okay. Then I will say, okay, that means that this same person, because his embedment, like this vector after transformation, is very close to the vector of already a person who is already in the base. But now imagine I have someone and I say, okay, it's very far from all these positions, from all these embedments. Therefore, I will know that this person is not there. And what I can do in this case, I can either, of course, from the security point of view, I will not allow him to enter the building. But what I can do, I can add him as another class in our neural network. So I just look at him once, and I already have a new class in my system. So that's why it's called one-shot training. So I do not retrain my model at all. So my model already exists, and I just add another class. So there is no retraining, nothing like that. So that's a very powerful tool for specific applications. And in this case, I will ask you, where do you think you can use it in mechanical engineering or civil engineering or material science? Any ideas? How can I use this so-called similarity learning in these domains? What would be your suggestions? Come on, anything. What would you suggest? Perfect. That's one of the very common application of that. So material recognition. So you look at the material, maybe even optically, and try to understand if it belongs to, let's say, the gold family or something like that. That's where you can use it, and it was used. This is very good example from the material side. It's really applicable. So any other examples? Come on, at least one more. Okay, let me ask in this case, and I will give you a hint. In structural health monitoring, how can you apply this approach, for instance? So, do you know how planes are getting checked during, I think, B check or maybe C check? I don't exactly remember which procedure. But how do you check if there is a crack inside? How can you check at least? Yes, exactly. So using acoustics methods. So you can actually sort of hit a little bit with a small hammer from one side of the wing and measure the response in another side of the wing. So if you have a very solid block, for instance, again, it's not a wing in this case, but you know that you hit it, you will get the same output. But if you have a crack there, you will have a very different signal. So in this case, you really just process the signal. So you may have the family of, like, you have a signal like that, maybe you have a signal like that, you have a signal like that, and you visually really cannot distinguish, like you cannot understand if they're the same or not. But you know from the research itself, let's say from the study, that all of them will correspond to a good state. So what you are doing in this case, and also you have something that also looks bad, and you have no idea why this is bad and this is good, but you know because you kind of have a controlled environment. When you did a crack and then you measure that, and you know that's a bad. And then what you are doing, you train your model using these two classes, class 0 and class 1, and you use the similarity learning. And instead of looking at this long signal, where I don't know 10,000 points in time, what you actually will distill from that, it's 10 numbers, like 20 numbers, this embedment. So, and then you look at these embedments, and the embedments for the good signals after training will be quite close to each other. So you don't know why particular this embedments, why particular, let's say maybe 1, 0.7, 8, whatever, will be your vector. But you know if you have the vector, and then you have an unknown signal, you have the plane, you want to test if it's good, if it's you can fly it, you can allow it to just to take off. You look at this embedment, you do a test, and let's say you have the embedment that will look something like 0.95, 0.67, and maybe 7.9. So now you just say, okay, I will just take a difference between them, and the difference will be very, very small. Therefore, I think it's good enough. It's really good. It basically belongs to the class of the good. But if you will have embedment vector something like 0, 10, and 100, I say, no, don't do that. We need to do a check. We need to understand what's happening with the plane. So that's exactly where you can use in health monitoring. Yeah, go ahead. Kind of, I would say, good luck with that, because you have so even when you check the data, you do not check the signal in the time domain. When you check the data, you probably do Fourier transformation. So you already do some processing of your data, and then any smart engineer will look at this and say, okay, we should not have this peak on the frequency of, let's say, 1 kilohertz. So you're doing some sort of the same thing, but without using machine learning. Machine learning will give you a little bit better range of the possible scenarios, because depending on the temperature of your wing, depending on the maybe amount of fuel into the fuel tanks, depending, I don't know, on a lot of parameters, degradation itself, your signal will change. So you need to look at specific numbers in the signal. And these numbers can be obtained using machine learning. Of course, I would say in aviation, probably they are not keen to use more machine learning for that, because it's very conservative area. But at the same time, even there, they already use it as maybe first guess, and kind of they will not allow your plane to fly if they see the positive. Like if they see this one, they will say, okay, but we still need to check. But definitely, if they see this one, they will say, no, stop. So kind of you of course, you are not replacing your regular procedures, like conservative procedures on the plane with this approach, but it can supplement it. You can add it a little bit more value. So, and that's exactly where in mechanics you can use it. It's a very good example with material detection. It's signal processing and something like that. So any ideas? So, and on that, I think we are in a good timing. We have a summary. So what we have learned today: we formally define such terms as domain and task. I think I failed a little bit to do it properly. So we learned that transfer learning is a very powerful tool enabling us to utilize pre-trained models and save a lot of time. We understand different types of domain adaptation, at least a bit. In many cases, it's possible to use synthetic data generation via simulations and then transfer learned model to the real world. And finally, we learn a little bit about quite interesting approach of CMS networks that enable us an effective solution of the classification problem via so-called similarity learning. And you have a lot of examples of similarity learning, especially in reinforced learning, but we will not go deep into this field. So on that note, I think the lecture is over. So thank you very much for getting a new knowledge from me, and probably you like the example with ants. I really like it. So a couple of words about the practice. So we'll have a practice this Thursday, we will play a little bit with YOLO model. So if you will record any video ahead of time for yourself, just to have something to play with, it will be cool. I don't know, 15 seconds, maybe 20 seconds, because YOLO is very fast. So even on your laptops, it should be almost real-time processing. Another thing, we will discuss Home Project 1, and I'm not very happy that I see only 11 submissions. So please do that, because if you will put your submissions for the Home Project 1 later and later, you already have a Home Project 2 right now. So it may be a problem. So please try to do it. We will take a look at this 11 and maybe a couple of more until the end of the Thursday. We'll give you feedback. I looked at them already a little bit and they look okay. So I think everything is good enough. So all these home projects will be counted as complete, and this is good for you. So you will be able to go to the Home Project 2. So yeah, please do that. It's important. And yes, YOLO will be on the next time. Then we will have another lecture on a Monday, and we still didn't decide exactly what we want. We have two options where they can give you generative networks when you learn how to generate new things, or we can talk a little bit about optimization. So we need to think how to do it properly, because I was a little bit surprised about your experience with statistics. So yeah, I expected that you had. Have you had a class on the statistics here? No, not yet. Okay. And in a bachelor, also not. Okay, good to know. Good to know. So in this case, we'll need to reorganize one of the lectures at the end. So yeah, thanks a lot for everything, and yeah, we'll see you on Thursday.